All right, so next, after we've done the gamma function, we're ready to tackle what are called Bessel functions. Okay, so Bessel functions are solutions to the differential equation. Bessel functions, I'm not sure why, but they're denoted j sub a of x and j minus a of x. And these are defined as, this is actually the easiest way to define them. These are defined as solutions to the differential equation x squared y double prime plus xy prime plus quantity x squared minus a squared y equals 0. Okay? And it turns out that if a is an integer, then these values are going to be linearly dependent. But if a is not an integer, so if a is not an integer, then these functions j sub a and j sub minus a will be linearly independent. Okay, so will be linearly independent. All right. What we're going to do is we are going to use the method of Frobenius to get a power series solution for these values. I want to just rewrite our differential equation. If I take this differential equation and multiply everything by 1 over x squared, what we're going to get is, we're going to study Bessel's equation, which is y double prime plus 1 over xy prime plus, if I take x squared minus a squared and divide by x squared, y, what we end up with is, so we get y double prime plus 1 over x y prime plus 1 minus a over x squared y equals 0. Okay. I want to point out that 0 is not an ordinary point, it's a singular point, but it's a regular singular point. It's a regular singular point. And that's because if I look at p of x, you get 1 over x squared, and that means that x times p of x, which is 1, is analytic. It has a power series at 0. And likewise, q was x squared minus a squared over x squared, or however you want to write it. And that means that if I look at x squared q of x, remember that you take x minus x naught times p, and x minus x naught squared times q. And in this case, for q, we get, this is x squared minus a squared. It's a polynomial, and therefore it's analytic. So this is analytic at x equals 0. Okay, that means that we're going to use the method of Frobenius, and we're going to get some solutions. Okay, so we're going to apply the method of Frobenius to get solutions. So we want to study, I'm just going to write it the usual way, the original way. I mean, x squared y double prime plus xy prime plus quantity x squared minus a squared times y equals 0. And we're going to assume that we have some sort of, I don't want to say power series anymore, but we have some sort of series solution y. It's going to be c sub n x to the n plus r, as n goes from 0 to infinity, right? This is the x to the r times our power series, right? So just remember that this came from thinking of this as x to the r times the power series. Okay, and y prime is going to be the sum starting at 0 of c sub n times n plus r, x to the n plus r minus 1, and y double prime is going to be the sum starting at 0 of c sub n, n plus r minus 1, x to the n plus r minus 2. Remember that for the Frobenius method, we do not shift the index for any of these, right? So these start at n equals 0 because the original started at n equals 0. All right, so now let's plug everything back in. So if we look at x squared y double prime, our ordinary differential equation is going to become x squared times this last sum. So the sum from 0 to infinity, c sub n plus r minus 1, x to the n plus r minus 2. Okay, plus x times y prime. Okay, x times y prime is going to be the sum from n equals 0 to infinity, c sub n plus r, x to the n plus r minus 1, plus x squared minus a squared times our original series. So that's going to be the sum from n equals 0 to infinity of c sub n, x to the n plus r. And that should all be equal to 0. So that barely fits on a line. But what we want to do is we want to just kind of move everything around a bit and see exactly how this is going to go. We can do all the usual stuff. So let's see. What I want to do first is take the x squared and the x terms and move them in the series. Okay, and then I'm going to split this as x squared times the series plus a times that series. So we're going to do a few things at once here, but what we have is the sum from 0 to infinity, c sub n plus r minus 1, x to the n plus r. That's going to be plus the sum from 0 to infinity, c sub n plus r, x to the n plus r. And then plus x squared times the sum from 0 to infinity, c sub n, x to the n plus r, minus a squared, remember a is a constant, from n equals 0 to infinity, c sub n, x to the n plus r equals 0. And we're already in pretty good shape. Okay, so we already have x to the n plus r, x to the n plus r, x to the n plus r, starting at n equals 0 for all of these. This third one, we're thrown off by that x squared term, right? And of course, if that x squared term weren't there, this would be a Cauchy-Euler equation. We could just do all the usual stuff, and this power series method is way overkill. But it's not overkill. This is really the only thing that we can do because we do have the x squared term, right? If the x squared term wasn't there, this would be easier, but it is there, so we're just going to deal. So what we're going to do is, let's see. First, let's factor out x to the r from all of our terms. So we're going to have x to the r, sum from 0 to infinity, c sub n plus r minus 1, x to the n, plus the sum from 0 to infinity, c sub n plus r, x to the n, minus a squared times the sum c sub n, x to the n, from 0 to infinity. And actually, let's move around, a little iPad magic here. Let's move around some stuff. I want this to a squared to be inside the sum. And then finally, we're going to be left with plus c sub n, x to the n plus 2, if we factor out the x to the r and move the x squared inside. And that's all going to be equal to 0. And again, we can do a few things. Let's take the first 3 terms and write them as a single sum. So this is x to the r. This is going to be the sum as n goes from 0 to infinity of, let's see, we're going to have c sub n plus r times n plus r minus 1 plus c sub n times n plus r minus a squared c sub n x to the n. Okay, and then plus our last sum, n equals 0 to infinity, c sub n x to the n plus 2. And then when n is equal to 0, notice that this will give us a constant term. And when n is 0, our smallest term there, that'll give us a square term. So I'm going to peel off the n equals 0 and n equals 1 term from the first sum. And when n is equal to 0, what we're going to get is we're going to have c0 times... I'm actually just a little bit annoyed by the fact that I didn't factor this, so let me go ahead and factor this. This is just my own little quirk here, but let's just factor out c sub n. And let's see, we're going to have c sub n times, this is going to be, I just want to simplify this a little bit. This is c sub n times, from the first two terms, we're going to have n plus r. Okay, so just to be clear about what I'm doing here, I have an n plus r and an n plus r, and we've already factored out the c sub n's. Okay, so I'm going to have an n plus r and n plus r, and I'm going to be left with n plus r minus 1. So it's going to be that part, plus 1, which is the part there, minus a squared. That's all times x to the n plus that sum from n equals 0 to infinity, c sub n x to the n plus 2. All right. And let's see, next, this is going to be x to the r. So from n equals 0 to infinity, c sub n, and then this is going to be written much nicer. So this is going to be n plus r squared, because this is n plus r times n plus r, minus a squared. So the difference of squares there, that works out very nicely. X to the n plus the other stuff. All right, now let's factor out the n equals 0 and n equals 1 term on the first sum. And so if n is equal to 0, what we're going to get is c0 times the quantity r squared minus a squared, plus, let's see, if n is equal to 1, we're going to have c1 times the quantity, let's see, r plus 1 squared minus a squared. And then we're going to add to that the rest of the sum that we already have. So plus this sum, as n goes from 2 to infinity, c sub n, n plus r squared minus a squared, x to the n, plus this last sum, which we haven't touched in a few lines here, c sub n x to the n plus 2. That's all equal to 0. And, from our indicial equations, we have a few things that can happen here. So from our indicial equations, let's look at this. This is going to be, by the way, I forgot when n is equal to 1, I forgot a term. Just looking back here. When n is equal to 1, I get c1 times the quantity 1 plus r squared minus a squared times x to the 1. I forgot the x to the 1. So I'm just going to put that in there. So what we're going to do is let's do two things here. Let's shift our index. Okay, so we're going to shift our index in this sum starting at 2. And then after that, we'll interpret everything. So we're going to have c0, r squared minus a squared, plus c1 times the quantity r plus 1 squared minus a squared, x, plus, let's see, if we shift from our sum starting at 2 to our sum starting at 0, this means that we're going to be looking at c sub n plus 2 times n plus r plus 2 squared minus a squared, x to the n, plus c sub n x to the n plus 2 equals 0. I forgot the n plus 2 over here. I just fixed it, but I didn't say it. So, all right. And now we're ready to look at our indicial equations. So our indicial equations are going to come from looking at c naught times r squared minus a squared being equal to 0, and c1 times r plus 1 squared minus a squared x being equal to 0. So really, I just want the constant to be 0. All right, so those are our indicial equations. Okay, so for the indices, indicial equations. Okay, so just just so we can write that there. So those are our indicial equations. And from the first one, from this top equation, we get that we have three possible solutions. We get that either C0 is 0, but we've already talked about ruling out that solution, specifically with the constant C0. If C0 is 0, then everything else is going to be 0 too. Okay, so we're going to throw that out. That's not going to be a good solution for us. And so all we're left with is that r squared minus a squared is 0, so that r is plus or minus a. Okay, so that has to be what's going on there. So if r is equal to a, then our second indicial equation is going to be a plus 1 squared minus a squared is equal to 0. And actually the only way that can happen is that if C1 is 0. So we do actually get that C1 is 0 because this reduces to 1 plus 2a times C1 is 0, and a is arbitrary. A can be whatever we want. Okay. You do actually, and I want to point this out, you do actually get something special and something nice if a is negative 1/2 or negative, so if a is negative 1/2 or positive 1/2, you get nice values for the for these Bessel functions. All right. But we're going to go, we're going to take this route. So we're going to say that r equals a, C naught is some unspecified value, say capital A. Actually, I don't want to say a too much here, so let's call this capital B. Okay. And C1 is going to be 0. And if we do this, what we need to do then is look at our recurrence that we're going to get from our other values here. So we're going to also have the recurrence that C sub n plus 2 times the quantity. Well, let's see, if r is a, then we're going to get, this is going to be n plus a plus 2 quantity squared minus a squared plus C sub n is going to be equal to 0. Okay, and so what that means is that C sub n plus 2 is going to be negative C sub n over this quantity n plus a plus 2 squared minus a squared. Okay, and if we want, we could factor that out if you really want. So this is a difference of 2 squares. So that means that this is going to be negative C sub n. We're going to have n plus a plus 2 plus a times n plus a plus 2 minus a. And so that really means that C sub n plus 2 is going to be minus C sub n over, let's see, n plus a plus 2 minus a is n plus 2. The other one is going to be n plus 2 plus 2a. All right, and so now let's just go to work and see what happens here. So we're going to go back. Remember that our sum started at n equals 0, so that's where our recurrence will start. So these are all going to be valid for n greater than or equal to 0. And if n is 0, you get that C2 is equal to negative C sub 0 over, let's see, if n is equal to 0, you're going to get 2 times 2 plus 2a. Okay, so it's going to be negative 4b over, negative b over 4 times 1 plus a. And C3 is going to be 0. Same with all the odds, because this is a second degree recurrence. C4, okay, what we're going to get for C4 is we're going to get, let's see, for C4 we're going to get negative C2 over 4 times 4 plus a. Okay. 4 plus 2a, rather. So we get 4 over 4 plus 2a. And if you want, you can factor out. This is going to be negative c2, so that's 4 over 1 plus a. This is going to be 8 times, let's see, if we factor 2 out, this is going to be 2 plus a. And so altogether, that's going to be negative b over 32 times 1 plus a times 2 plus a. And in general, what we're going to get is if you look at the, our term here, c sub 2n, you're going to get some formula for it. And really what we're going to do in the kind of canonical choice that we're going to make is we're going to choose to let our value b can be whatever we want. But typically people choose b to be 1 over 2 to the a, gamma of 1 plus a. Okay, so that's kind of the relationship that you're getting here. Okay, 1 over 2 to the a times gamma of 1 plus a. And so what that means is that c sub 2n is going to look like, negative 1 to the n over 2 to the 2n plus a, n factorial, gamma of 1 plus a plus n. And so that's going to be your coefficient, and therefore your Bessel function, j sub a of x, is going to be the sum from n equals 0 to infinity, c sub n, x to the n plus r. And we're going to do the usual trick where what we're going to do is we're going to write this in terms of the even and the odd values of n. So it's going to be c sub 2n, x to the 2n plus r, plus the sum from 0 to infinity, c sub 2n plus 1, so c sub 2n plus 1, x to the 2n plus 1, plus r. And of course, all the odd terms are 0, so that means that those are all gone. And what we're left with then is j sub a is going to be this power series. So the sum from n equals 0 to infinity, negative 1 to the n over n factorial, gamma of 1 plus a plus n over 2, or I'm sorry, 1 plus a plus n, times x over 2, 2 to the n, x over 2 to the 2n plus a. Okay, and that's quite something. I don't know what, but that's something. And so this is the Bessel function with the value a. And next, if you look at the Bessel function, I'm just going to totally cheat here. I want to point out that I actually skipped a few steps along the way that you can go ahead and fill in if you'd like. Coming up with this exact formula, figuring out exactly how to get this in here, how to get the quantity in that form. But I'll let you do that on your own. And remember that was just one of the solutions of the indicial equation. Right, so j sub a, and then j sub minus a, if we do this, we're going to get negative 1 to the n. Basically, it's going to be the same thing, except all of our a's are going to become minus a's. So you get 1 over n factorial, gamma of 1 minus a plus n, x over 2, and then 2n minus a. Okay, and those are going to be your Bessel functions, j sub a and j sub minus a. And what I have is some of the values here. This is actually the picture that you look at when you log into our course, is this actual picture. And these are different Bessel functions for different levels, right, for different values of a. Okay, so j sub 0, j sub 1, j sub 2. All right, and there we go. So those are Bessel functions. Bessel functions come up in lots and lots of places. And the easiest way to define the Bessel function is actually as the solution to a differential equation. Okay, so there we go. So there's Bessel functions. I don't think I'm going to give you any homework questions that deal with Bessel functions. This was just kind of informational. Bessel functions are really hard to work with, as you've undoubtedly noticed. But they're important enough that I at least wanted to mention to you what they are. So there we go.